Vinci, Apocalypse Now, and many, many other extraordinary films. Murch, not surprisingly, has some history with our film department, and so it's especially meaningful to have him here with us. While beyond his extraordinary career with film, Murch also has had a decades-long passion for the field of astrophysics. That's the title of the book. And rather than my attempting to say anything about that, I will leave that to the book and also to the conversation that we're about to hear. So please join me in welcoming Lawrence and Walter.
Thank you. Ordinarily, Walter and I have been on tour. Ordinarily, we do a slideshow, but the light was thought to be right. This puts me in, and by the way, it's our fault that we're in here and not in the theater. Anyway, but I was once in a situation not unlike this, where I had in all things, I had a slide carousel, remember slide carousel? And I was going to talk about a premiere at the Huntington in Pasadena, and I bought the carousel, and they could not find a slide projector at the Huntington. But I was lucky. It was a thing for university art book editors, and there were 800 of them in this long, thin hall. And luckily, I had my trusty complete works of Vermeer book. And so I opened it up and I said, what I want to talk about today is this one here. People that have with it. Anyway, so look at that. But you're going to have to live with my very sad versions of Walter's extraordinary charts. Let's see. I think we'll just dive right into it right now, actually.
Sure.
And, we have various patterns that we do, but this is a relatively short song. So, why don't we start with this picture here? I'll stand over there.
This is definitely old school, but that's just fine.
We're both very analog today. Okay. So, there's what you got.
So here, Lawrence's expert rendering of Galileo's drawing that he made in 1610. These are the first.
I did it a few hours ago.
Right, yeah. These are the first objects seen by a telescope that are invisible to the naked eye. And Galileo in 1610 was the first person to have the intelligence and presumption to take the newly invented telescope and point it at space. And he looked at Jupiter, because Jupiter is the largest of the planets, and that it was particularly bright that evening in 1610. And he was astonished to see what he called 4 stars around it. The next day, he looked again, and the stars were in different positions. And this is when the hair on the back of his neck presumably went up, because he realized that these were satellites of Jupiter. And if that was true, then the whole idea of crystal spheres had to be thrown away, and this was another certification of Copernicus's idea that the sun was in the center and the Earth went around the sun like all the other planets did.
So just before we go on to the next thing, I should mention that as you tell from this kind of stuff, Walter knows stuff. In addition to being an as was said, this hugely admired film editor and seems to be working on films all the time, he is incredibly well read. And one of the ways that this comes out is that when you're visiting him, toward the end of the visit, he'll take out a little pouch like Gandalf's pouch, and he lets you reach in and pull out a fortune cookie piece of paper, except that it has quotes from a whole range of people, which give you some idea of his reading. And I thought I'd just read you some of the ones that I've gotten over the years to give you a sense of the range of Walter. The great battles are always waged where the maps overlap. Napoleon. Translate the invisible wind by the water it sculpts in passing.
for song. Tell the truth as you see it, let beauty take care of itself. Truth never comes into the world, but like a bastard to the ignominy of the one who brought her forth. John Milton. If at first the idea is not absurd, there is no hope for it. Einstein. Music is the pleasure the human soul experiences from counting without being aware that it is counting. That's Leibniz. Seek simplicity but distrust it. That's Alfred North Whitehead. Science is the belief in the ignorance of experts. Richard Feynman. Start every film with one certainty and a million questions, and end every film with a million certainties and one question. Anyway, so the point, coming back to this is the sort of thing that Walter knows about, and then in 2008,
there's a lovely picture that you can find online of this drawing that Ren expertly simulated, but it is of a star pretty close to us in galactic terms, 129 light years away. Very new. It was born as a star only 30 million years ago. And it has 4 photographable planets around it. And this is the first time we've ever photographed an exoplanet. Otherwise, we depend on circumstantial evidence, the dimming of the star as the planet passes in front of it, or the wobble of the star as the planet goes around it. But in this case, because the system is so huge, we can actually photograph it. And there are 4 planets. Galileo named his planets around Jupiter. He named them for the lovers of Jupiter, Io, Europa, Ganymede, and Callisto. But we today have the romantic notion that we should name them B, C, D, and E. Someday they may require the names of lovers, or maybe these are the lovers.
now if I had all the time in the world, I would have given you how far in miles, or in astronomical units each of these are, but they're very far from the stars. Is that correct?
Right. The furthest one is twice as far from its star as Pluto is from our sun. And the next inward C, the C planet, is basically right where Pluto is, so you can gauge some sense of the dimensions. And the planets themselves apparently are 1.5 times the size of Jupiter, so they're very big.
Which is why we can see them.
Right, exactly. And the curious thing about them is that their orbits proportionately are identical, given 1% variance, to the orbits of the moons of Jupiter.
All this way from here? 1, 2, 3, 4.
Yeah. So that would be Io, the equivalent of Io, that would be Europa, that would be Ganymede, and that would be Callisto. Even though the systems are 5,000 times different in scale.
And by the way, these are very bad approximations of what the distances actually are, but the point is they are identical. Weird.
And here we're comparing what's technically known as their semi-major axis, easily understood as the average distance, an idealized circular orbit at an average distance.
Since the orbits are usually elliptical, but average it out, that's what. And it's weird because something else happens too when we, with this same set of proportions.
Yes, you could also superimpose here where the D planet is, you could superimpose the Earth. The C planet would be Mars, and the next planet out would be the center of the asteroid belt, we call it Ceres. So there are these, despite the vast differences in location and scale, there are these fundamental resonances in the orbital comparisons of the orbital ratios of very, very different systems.
Now, ordinarily when we do our slideshow, he
expertly slides these things on top of them, and when he slides the earth on top of it, he goes, oh! This is kind of amazing. But there's a warning.
And this is a very useful word in many different aspects of life. Apophenia, which I bumped into as I was doing all of this research. And it's the tendency human beings have to see patterns where none exist. So if you see the face of Jesus in an English muffin, that's apophenia. And, but on the other hand, harnessed correctly, just shy of apophenia, that represents one of the ways at which we would define science, certainly, is looking for patterns where there doesn't seem to be a pattern. And in film work, we deal with this all the time. Editors especially are looking for patterns within systems that are, the shooting is sometimes very chaotic, and we have to find the hidden patterns at the most superficial level and then as deep a level as we can go. But this is sort of a memento mori to tell myself and you that I'm very aware of the sometimes thin ice that we launch out when we start looking at these things.
So Walter, how did you get into this particular frenzy, which is now 20 years long?
This, I should say that in working on a film, I work very long hours and I'm completely immersed in the world of the film. And when I'm not in the world of the film, I find it very hard to look at other films or television or anything. I like to read, and I mainly like to read science. It doesn't matter what kind of science, biology, astrophysics, cosmology, physics, popularized. I'm not a scientist. I didn't get that degree. I don't have the chops to read the source material always. But on one film I was working on in England, I was reading The Sleepwalkers, which was Arthur Kessler's wonderful book. I would recommend it if you hadn't read it, on the developing history of humanity's concept of the universe, from the ancient Greeks, ancient Egyptians, up to and through Newtonian. He stopped at that point, mainly focused on Copernicus and Kepler. And in a note at the back of the book, he mentioned something that I must have heard of before, but I really focused on it this time, which was Bode's law. Bode himself, he was a German scientist, sort of the Carl Sagan, Neil deGrasse Tyson of the late 18th century. And he made an observation, courtesy of an observation of another scientist, Johann Titius, also German, that if you take a very...
Before you come to that, Johann Titius was translating the natural history of Charles. By the way, Titius, because his name was deep and Marx's decline into not only not true pure numerology, but it's like with cooties. Nobody, well, you should describe how it...
Yeah, but it had a function, and to this day, if you take Astronomy 101, hoping to become an astronomer, you will encounter Bode's law as a sort of aversion therapy. Maybe in the second month, the law is taken out of a paper bag and dangled in front of you seductively, and then the teacher will beat it to a pulp with the stick called numerology. That it seemed to be tantalizingly true, and then it didn't, it wasn't. And not only is it not true, but the very way that we think about this is also not true, and you mustn't think this way if you want to become an astronomer.
And this is so much the case that in 1930, nobody even bothers to notice that Pluto is exactly where it's supposed to be.
Well, Pluto is where they thought Neptune would be, within 1.5%.
So anyway, Walter is Walter, and he reads that this is not to be looked at and blah, 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 and that's fighting words for Walter. So down the rabbit hole he goes. Let's see here.
And one way of thinking about, or the way I've organized what Walter's been doing for the last 20 years is going back to Gauss's objections. And they would all have to be dealt with if things were going to be, if we were going to get anywhere. So maybe we can start with Walter. How do you deal with the problem of negative infinity to
What's
zero?
the thing that you didn't show?
That was what I showed before. Before Gauss.
Okay.
So, I will try to, while you talk, I will try to illustrate what you're saying. Go ahead.
So I never took Astronomy 101, and so I didn't have that Bode's law with a circle and a diagonal through it branded on me, and I blundered deeper down the rabbit hole. I also have a fondness for the underdog, and I thought, here's something that describes all the way out to Pluto, including Pluto and Ceres. There are 10 objects here, and 9 of them fit surprisingly well. One of them doesn't fit. What if we just took that one that didn't fit and set it aside and think about how we can improve what is left?
So Neptune is in detention for the time being.
Right. Right. It was like a bad boy in school. But Neptune, no, you didn't. For some reason, you're not obeying the rules, so you go in that room and we'll deal with you later. So Gauss's first objection was this jump, and just for the hell of it, I said, well, let's remove the jump. Let's make that exponent go from minus infinity to plus infinity.
So right now, if Mercury, for the sake of this discussion, is at the limit of this rule at minus infinity, and Venus is at 0, and then Earth is at 1,
Right.
you're saying that you could have all sorts of orbits here, starting from infinitesimally small, getting doubling and doubling and doubling,
Right.
and they don't,
We're familiar enough now, thanks to the discovery of the atom, with this concept of virtual orbits, which they weren't in the middle of the 19th century. The hydrogen atom has surrounding it a mathematically predictable series of orbits that are potential but not occupied at any one time. It just depends on the amount of energy that the one electron going around the proton has absorbed. If it absorbs more energy, it jumps instantaneously to a further out orbit. If it loses a photon of energy, it jumps inward. So we can, in our minds, imagine these potential orbits in a way that somebody in the middle of the 19th century could not, because they didn't even know that atoms existed.
another way of putting it, by the way, is that the current model isn't so much a clockwork model as a statistical range of, would that be correct, or how would you?
Yeah, it's, I mean, hidden even within the original formula are all of the potential orbits from Pluto on out ad infinitum. Obviously, that's impossible. We can't have planets orbiting the sun out beyond the Milky Way. But what this formula then does is predict a series of orbits which have a descending radius coming to a limit. And we're familiar with this concept of the exponential limit. And so, why not? And I should say also that this is exactly what the formula that we encounter in music is. That music, the law of octaves in music, is that whatever note you want to say times 2 to some value, raised to some value n, and n is defined as from minus infinity to plus infinity. And depending on what kind of music you're talking about, then that's the value that you will get. And obviously it extends into impossible realms at either end.
So the next problem that you were faced, and by the way, we'll see whether these get filled.
Right, that was the challenge, that in the solar system, which is one system, those orbits are virtual and unoccupied because of something. But maybe if we look at other systems, and now that we have from Voyager and Hubble and the Kepler telescope, we have all of this data on other orbital systems in the Milky Way, us included. Maybe we'll find orbits where these systems where these orbits are in fact occupied.
So what about this gnarly formula? Do you have a way of getting out of that ugly thing?
Right. The original Titius formula and Bode's version of it set the Earth's value at 1. And this is sort of a hidden an egocentricity, because we're the Earth, we deserve to be 1. And in a sense, it's not totally dissimilar to the feeling back in the ancient world that the Earth is the center of everything. So the Earth was blessed in this case with the value of 1, which means that everything else is compared to it. And in this case, what Ren has drawn is Bode's law says that there is an orbit occupied by Mercury, which is 40% of the Earth's orbit. And then there is another, next orbit is 70% of Earth's orbit, and that's where we will find Venus. Then Earth is 1. And then there is an orbit which is 160% of Earth's orbit, and that's where we find Mars and so on. But wouldn't it be better, mathematically simpler, since we're dealing with a geometric progression, to begin this limit at the value of 1? And in that case, we just transpose everything, like transposing in music from one key to another. Mercury now becomes 1, and Venus now becomes 1.7? 1.75. 1.75.
Right.
And then Earth is 2.5. Mars is 4, and so on. Ceres would be 7. The values relative to each other are exactly the same, it's just they're simpler. And we got there basically by doing bone simple multiplication, multiplying the formula by 2.5. But if you do that, the formula that Bode came up with becomes much simpler.
It becomes 1 plus
2 to the n
times
3.
That's prettier.
It's prettier, and we like the numbers 1, 2, 3. They're very basic. And it turns out, we may get into this later, that there is a physical correlation for each of those numbers, that they're not arbitrary, that they have a function in describing the physical reality.
And one of the things here is that, one, do you want to talk about beta here?
Yeah, basically the formula says the orbits do not start, obviously, in the center of the sun. Everything, the distances are measured from the center of the sun, but the orbits don't start there. They have to start at some distance from the sun. And they can't start too close to the sun, otherwise the object in question would be just sucked inside. So if they start, stable orbits have to start at some remove from the object around which they are revolving.
And that would be the 1 of this formula. And then you start having a doubling sequence.
Right, and then from that point, which is some distance removed in space from the center of the sun, the orbits double in size. And then the number 3 puts you at the arithmetic midpoint between 2 predicted.
Okay, so we'll talk about that more a little bit later. What about this problem of not enough instances?
Actually, the formula for the octaves has an exponential value which is not restricted. Excuse my sunglasses, I forgot my real glasses. But it turns out that there is a similarity, a formulaic similarity between Bode's law and the laws that we observe in music. And if I can find it here. So the music is the linking of a number of vibrations per second with and assigning a certain number a value, a note value. And for instance, 330 vibrations per second sounds like this. That's the note E at 330, and if we go up to 528 vibrations per second, we get that.
What is that?
That's C, C above E, and then
Do we want to illustrate that first? That's
if we hear them together, it works like that, it sounds like that. So,
we can also do the
what we're dealing with here are numbers, and numbers in some kind of relationship to each other. The number of vibrations in E divided into the number of vibrations in that note C is 1.6.
But you could also draw it like this, that there would be a circle, and you'd have 330 units, 528 units, and they would have, and that would be the sound.
And in fact, making that leap, that is the predicted ratio in Bode's law of Earth's orbit to Mars's orbit. So if you wanted to simulate the predicted orbit, courtesy of Bode's law of Earth and Mars, you would hear the notes that we just played for you. And I should say that where you begin, I chose E and C, but I could have chosen any other vibration or note. What's important is simply the proportions relative to each other, which is in music the same thing as transposing from one key to another. You can have the same piece of music, and then thanks to the even tempering, you can transpose from one key to another, and it sounds the same.
Do you have another example?
Yep, go on there. So here are the 4 orbits of Jupiter's moons in musical terms.
For example, I mean, we are doing cutting-edge 18th century science here, but in the 17th century, Kepler was talking about music of the spheres in terms of the sounds that the ellipses would create, speeding up and slowing down and so forth. This is a different kind of...
Yeah, Kepler, I should say, was one of the greatest scientists ever, both in terms of what he did and how he did it, and his personality was fascinating. But he didn't particularly like the fact that he discovered that orbits were elliptical. He thought, why would God make elliptical orbits? It just doesn't, they're kind of lopsided. He went so far as calling them a cartload of dung in one of his most famous books. So he was nonetheless enough of a scientist to say that they are elliptical, and that this is a mystery. And he then formulated what were known as the Rudolphine tables, which were used until the middle of the 19th century because of their accuracy of solar system phenomena. And but he didn't know why it should be. The why question was left empty. Thankfully, along came Newton in 1666 to 1690, those years that he was working on the Principia, and he said, thanks to having invented a branch of mathematics, calculus, he said the reason that they're elliptical is because of universal gravitation. That every object in the universe attracts every other object by its gravitational moxie, and the planets and the moons and the comets and the suns and the stars all are all dancing to this tune, and he was able to write out the tune in a very simple formula, Newton's famous formula, which you encountered in high school. But he said, I don't know why it works. Why should it work? Why should gravity, why should the mass of an object across empty space affect the behavior of another object? And writing in Latin, as they all did back then, he said, non fingo hypothesi, meaning I will not make a hypothesis about this. I'm just telling you how it works, not why it works. So he kicked the can down the centuries, and all of the 18th century and all of the 19th century, 200 plus years had to pass before another genius came along, Einstein, and said the reason is that gravitational objects distort space-time, and what we think of as gravitational force is the objects trying to find the most efficient way of dealing with this distortion in space. And so on. So there's down the centuries, there is this dance of utility and the how and the why, and one of the things that affects Bode's law is that we don't know if it is true, we don't know why it is true, and it is not useful. Newton's laws were immediately useful because we could use them to calculate the trajectory of cannonballs and kill more people that way.
And Einstein got us the atom bomb.
And then Einstein invented the atom, the science that allowed us to make the atom bomb. So,
and what possible use is Bode?
Right, Bode has not yet, nobody's figured out yet how to use Bode's
No,
law to kill
weaponize
people.
it. But there is an interesting thing about the why, because this is a hint of the why is provided in the musical analogy. Now, by the way, this is not actual sounds happening in the world. This is statistical sounds. It's the ratios are statistical. But starting at a beta distance, there is this doubling. Now, while I draw this little thing, you need to explain about ants, because I have to have a little time to do this.
You keep
I
wanting
know,
me
but
to
they're,
point
so,
to the ants.
but they're so good. So tell about the ants.
Okay, this is, there's a little break here. Don't do this at home, although no ants will be harmed in the process. But you can find things on YouTube that do this. What you need is a microwave machine, some adhesive tape, and a cup full of ants. And if you take the little carousel in the microwave down so it doesn't rotate, and then pour the ants into your microwave, hopefully a disposable one, and then turn the microwave on, you will see the ants immediately move out of the way of the blade-like force of the microwaves into an area where the microwaves aren't. And so you can visualize the patterns of microwaves by the behavior of ants. So, curves.
In the slideshow, we have a really pretty thing that makes it almost like a frisbee as it goes around. Even that's not exactly right. It's really, if you think about it, hot. And by the way, from my point of view, a fair-minded inquiry, in the sense that I really believe that the astronomers are right, that you can't look at this kind of stuff. Outsiders aren't equipped to do it. That you have to protect truth. You can't just go around having these things. But having said that, it is also the case that until 60 years ago, 70 years ago, this is not how science was done. Science was not done by tenured professors. It was done by all the great breakthroughs in sciences were done by amateurs.
The word itself, scientist, was invented in the 19th century. Before that, if they were called anything, they were called natural philosophers.
And in any case, so the book becomes kind of a comedy about who gets to say what's interesting, what's not. And it also, in a way, is a note put in a bottle and sent out into the world in the hope that perhaps there will be some who really want to work with it. A very interesting problem is you would think that this would be something that a graduate student, for example, might want to take on. As there's enough here to work on and really push it further and see whether it's statistically valid, all kinds of things that Walter can't do. But no graduate student in their right mind would take this on, because they would be slimed with tedious code and would never get a job. Similarly, people, and by the way, in fairness to the scientists, they're very busy. There are all kinds of cranks, and this is a crank magnet, this particular tedious code. So anyway, it becomes quite complicated and quite interesting, but also maybe we'll see whether it gets any further. They keep on saying that all Walter has to do is write a peer-reviewed paper, and they'll look at it. But that's precisely the kind of Mandarin mathematics and kinds of things that Walter admits he can't do. And Walter constantly says it may be apophenic. I'm willing to.
I should say I'm not, as I said, Ren is the entomologist and I'm the bug. I'm not, rattling the cages, the bars of my cage in frustration about this. I would love to talk to people, but I've been perfectly happy pursuing this in between films for the last couple of decades, and I've learned lots of stuff along the way, little side channels from the rabbit tunnel. And I would be happy if there was some movement in Titch's Bow, because I think something is going on there. And it seems to be happening now vis-a-vis the paper that we were just talking about from Australia, papers. And is it true? I think something's going on there. What is definitely true is that the discovery that I made, which may be of historical interest only, is that the original Titch's Bow formula had these defects in it, which were there because they were thinking of only the solar system, and that there were these peculiarities related to giving the Earth the number value 1 and that little jump in the formula. Once you remove those two things, everything, the formula relaxes, and it's much more friendly to be exported to other systems for analysis, and the discovery that is a series of harmonically pleasing notes to human beings. And the idea that the solar system and orbital systems have music embedded in them is kind of a delightful idea that, as I said, was inherent in the very first scientific discoveries made back by Pythagoras, 600 BC. For many years after Kepler, that whole idea was abandoned, and now, at least in a side channel, it may be returning.
I should say, by the way, that I love that we're having this conversation in the middle of the hippie modernism. I'm going to throw this open to questions. We'll do a few questions and then we'll come up here. I would just ask one question that occurred to me. The way you just phrased it right now, that it is strange that the solar system seems to be, that these things are in ways that are harmonically pleasing to us, is the suggestion that creatures that grew up in solar systems like this would have this notion of what is pleasing, or rather than, I mean, how is that possible?
No, I think it's just that we lived for many years in jungles where there was bird song, and birds obey the laws of music, and an object that is resonant, that gets struck, obeys the laws of overtones and harmonics. It vibrates at a fundamental frequency and vibrates at slightly less energy at double that frequency, slightly less energy at triple that frequency, and so on. And that's what gives objects and musical instruments their particular character, is the fingerprint of those energies as they finally reach dissipation. That's just the world, it's just the physics that surrounds us. The physics that surrounds us is harmonic, and this is just another example. It isn't musical, as Ren said. It isn't musical in the sense that the planets are not generating sounds, but they are at what are musically significant ratios to each other.
So let's take a few questions. But you have to stand up and you have to yell. Jupiter now.
The Jupiters?
Yeah, right.
And it sounded to me like it might be a seventh chord. Is it
The seventh chord.
Thank you very much. Exactly that. The seventh chord is something that shows up, which is interesting because it's kind of a jazzy chord that in classical music, it was something that you avoided because B flat wasn't really considered, in the key of C, B flat was not really respectable. But now we use it all the time, and it's just interesting that here it pops up in orbital systems.
Over there?
Can you clarify,
Yeah.
do you say this also happened on the atomic scale with atomic orbits? Electron orbits?
Does it happen with atomic orbits too?
Electron orbits?
Yeah, the atomic orbits are a different system. The math behind it is a different system. Here,